Let's take a look at an example of using Riemann sums to calculate one of these definite integrals. So now that we see this notation before, this is the integral from -3 to 2 of 3x dx. And we'd like to use Riemann sums. So remember, Riemann sums, that's just the same thing as using limits with our rectangles getting smaller and smaller in width. Now remember, with Riemann sums, you can pick any choice of endpoints and any way to choose the width of your rectangles, or in other words, a partition. You're partitioning this region into these different rectangles. Choose any of those. So for our solution here, we said we can pick any way to partition our interval or any type of way to describe the widths. The easiest way to do that is the first thing we did in this class. Oh, I guess first thing we did with these is that we have the same width of all of these. So we're going to pick equal widths. Or this is also called the uniform partition. So we're partitioning our interval into these into these n regions where they're all the same. So pick equal widths where our delta x is going to be b minus a divided by n, but our b minus a in this case, we know what these are. This is going to be, our a is -3, so this number here, this was our a, and this number up here is our b. So I have 2 plus 3 divided by n, so I have 5 over n. So you pick your widths. I'm pretty much always going to be picking this equal width, this uniform partition. Then you can also pick the endpoints. And we said any endpoint will work for us. So I'm going to pick the right endpoints. So remember, these c sub i's, we define this as a plus I times delta x. So our a in this case was -3. Our I sticks around. Our delta x we said was 5 over n. So you might be thinking, well, what's the purpose of calling this Riemann sums? It just allows you that if you want to do something different, you can. Now, this is much more definitely for the theoretical side of math, and so more advanced calculus, like when you're proving things, then that's when you start to look more at the special things. But for right now, you're basically just redoing the same things that you did before, just being aware that Riemann sums is that key phrase that you'll see. Okay, so now what we're going to do is we're going to look at this area. We said the area formula was the limit as this largest width goes to 0 of the sum from I equals 1 to n of f of c sub I delta x sub I. So we have this width of all of these. So we have this area of each of these. Remember, it's the height times the width. But for this notation, we don't need this fancy notation anymore. We'll just go right back to what we did before. And so this is going to be the same as the limit as n tends to infinity of the sum from I equals 1 to n of f. Our c sub i's is -3 plus 5i divided by n times our delta x. They're always the same for every I, so it's just 5 over n. Now we plug this into our function. Our function in this case is 3x. So this expression here, this is 3x. So I have the limit as n tends to infinity, the sum from I equals 1 to n. I have 3 times this. This is my x. So I have -3 plus 5i divided by n times 5 over n. And then we're just working with this sum the same exact way that we worked with all the other sums. We have the limit as n tends to infinity. I pull out my constants. Here I have a 3 times 5 over n. I pull out a 15 over n. And I have the sum from I equals 1 to n, -3 plus 5i divided by n. And then I separate this into two sums. So I have the limit as n tends to infinity, 15 over n times the sum from I equals 1 to n of -3, plus, at the same point when I take this sum, I'm just going to take out the constants as well. So I'm just going to skip a step, take out the 5n, sum from I equals 1 to n of I. And then we use our formulas that we know. Limit as n tends to infinity. 15 over n. Formula for this is going to be negative 3 times n. The formula for the sum of i's is going to be n times n plus 1 divided by 2. So I have plus 5 over n times n plus 1 divided by 2. Then I can multiply this 15 over n inside. So I have the limit as n tends to infinity. I have negative 45n over n plus here. So now if I have 15 over n times this 5 over n, I'm going to have a 75 over n squared times n plus 1 divided by 2. So I have the limit as n tends to infinity. I'm going to have this limit here. We can just cancel the n's. So this could be the same as negative 45. And here I can cancel one copy of the n with that n. So I'm going to have 75n plus 75. So if I distribute the 75 into there, divided by 2n. Now, this limit we know is equal to negative 45. This other limit, the limit as n tends to infinity of 75n plus 75 over 2n, well, this limit, again, by L'Hopital's rule, we can see that this is going to be the same as 75 over 2. So this is going to be negative 45 by L'Hopital's rule, negative 45 plus the limit as n tends to infinity of 75 over 2. So I have negative 45 plus 75 over 2, which this, if I find common denominators, this would be over 2. This would be 90 over 2. So negative 90 plus 75 would be a negative 15 over 2. Or in other words, this is negative 7.5. So this, what I have just done, I have done a Riemann sum. That's allowed, right? Because I said as long as my function is defined on this closed interval and this limit exists. This limit exists. This function 3x is obviously defined everywhere. But what did we say this number corresponds to? We said this number corresponds to an area. I have just said that the area is negative 7.5. Immediately, you should have sirens go off in your brain of, wait a minute, wait a minute, wait a minute, wait a minute. That's not right, right? I've always been taught that areas must always be positive. So what do I do with that negative? So let's visualize what we have done. So we have looked at an area of a function. So our function is 3x. We've looked at it on the interval from negative 3 to 2. So from 0 to 2, this would be what we would expect to find. From negative 3 to 0, well, our function is negative. So what does this mean? Well, we actually found this. So we have found this area. This is what's somewhat being defined by this. Now, because these are both triangles, we could easily figure out the area of both of these triangles. So since this is the function here, 3x, this would come up here to 6, and this would come over here to negative 9. So I'm going to take 1/2 the base times the height. So in this one, I'm going to have my width over here is 3. This is going to be 9. So I multiply that, I get 27. I divide that by 2, and so I get a 27 divided by 2. Here, if I take the area again, which is going to be 1/2 the base times the height. Height is 6, this is 2, take 1/2 of that, I get 6. Now this number here is going to be 13.5. So if you have 13.5 and you have 6, and somehow our answer here is negative 7.5, we should maybe see how these could relate to each other. That if this here was actually a negative, and this is really a positive, well then if I add these two together, then I get negative 7.5. So that is what's taking place when we look at this area, this definite integral. We have different things appearing if we are above the x-axis or below the x-axis. And so we have this important result here that the definite integral, if f is greater than or equal to 0 on the interval, is a positive area. If f is less than or equal to 0 on the interval, so what I'm saying here is that if my function is going to be above the x-axis, so it's a positive value, I have a positive area. If I am below the axis, I'm below the x-axis, I'm negative on this interval, what this gives us is we get a negative area. So then, if we have to combine all of these, if we have both positive and negative area, what this gives us as a big result then is the integral from a to b of f of x dx can be seen as the net area. So that's truly what we're finding. When we looked at areas in section 4.2, we had to make sure that it was always positive. We only defined it for positive functions. But if I allow myself to potentially be negative, then this no longer makes sense anymore because it doesn't make sense to talk about negative areas. But we'll see why we can use that in the future and why this idea of a net area is very powerful. But just think about that. If you get negative numbers in this, that is okay. That just means that there is more area below the x-axis than above the x-axis. But in all of these, they're finding the area between the function and the x-axis. So that's what we're looking at. Below the x-axis, negative. Above the x-axis is positive.